Hi everyone, and welcome to today's Physics Daily Booster. This is number 16 in our Paper 2 series, and although it is not listed on the advanced information for either foundation or higher tier physics, that doesn't mean they're not going to put at least some questions on this topic on the paper. We are going to continue with our journey through space and the universe. What we're going to focus on first of all then is our solar system. So our solar system is going to consist of our sun, which is a star, planets, the spherical objects that orbit around the sun, moons, which orbit around the planets. There are minor planets, which are basically the things that aren't planets or comets, but still orbit the sun. So think dwarf planets like Pluto, asteroids, etc. that could have fallen into this little category. And then we have comets themselves. These are made of ice and dust that will be orbiting the sun on some rather large orbits in some cases. So, if we think about our solar system, I would hope from your Key Stage 3 knowledge, then you know the order of planets working out from the sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Those first four, Mercury, Venus, Earth and Mars, are the inner planets. So they're all rocky, they all have an atmosphere of some description, but they have some key differences. First of all, if we think about Mercury and Mars, they only have very thin atmospheres. Venus does have an atmosphere, but it's mainly carbon dioxide and not particularly hospitable because it rains sulfuric acid on that planet. So again, not the kind of place you want to hang out. Earth itself is obviously the one with the atmosphere that suits life as we know it. We can then compare the number of moons. We have one moon, hopefully you know that much. Mars has 2, and then Mercury and Venus, no moons. We then have our 4 outer planets, Jupiter, Saturn, Uranus and Neptune. When we think about Jupiter and Saturn, these are gas giants, whereas Uranus and Neptune are ice giants. Called giants because these planets are huge, okay, much bigger than us. All of them have rings. We know we only think of Saturn as rings, the others just aren't as famous with their rings and are spectacular. And they have lots of moons, and by lots I mean lots of moons. Another key feature of our solar system is the asteroid belt. Now the asteroid belt itself is located between Mars and Jupiter. So the asteroid belt is basically made up of these lumps of rocks or asteroids that were left over from the formation of the solar system. And also within the asteroid belt, this isn't a tiny little thing, it's quite big, then we have a dwarf planet called Ceres. So what we find is that between the inner planets and the outer planets, we have the asteroid belt. What we're going to look at then is how we actually form these different stars. And the key word in all of this is going to be gravity. I guarantee that if there is a question to do with formation of a star and you don't use the word gravity at least once in your answer, you've absolutely thrown away a mark there, because gravity is core to virtually the whole thing. So what we'd have as a starting point then is a huge cloud of dust and gas. Now, even those tiny particles of dust and gas have a force of gravity between them, and they pulled those little particles of dust and gas together. As this was happening, then what we find is the core of this gets very hot. The hotter it gets, the faster the particles moved, and eventually they were moving fast enough for nuclear fusion to occur. Think back to our work in P6, nuclear fusion is where we are joining 2 nuclei together. Now, what we find is we end up getting to a point eventually where the force of gravity pulling particles inwards and the expansion of hot gases pushing outwards is in balance. And that is currently where our sun sits, in this lovely balanced position. What we need to know then is not just about our sun, we need to know the life cycle of all stars. Good news, they all behave in a pretty similar way. The formation of all stars, regardless of the size of them, is going to be the same. We start off with a huge cloud of gas called a nebula that's pulled together by gravity. That large ball of gas forms at the centre of the cloud, gets denser, pulls more gas in, the ball gets hotter, and eventually we form this thing called a protostar. So this is where we've got a very hot ball of gas that's still pulling more gas together. That protostar continues to get larger and larger until we get to that point of nuclear fusion. So when we're at the point of nuclear fusion, we're at that balance between gravity pulling the gas in and the expansion of the hot gases pushing out. That is a main sequence star. That's the stable part of the life cycle and where a star can sit for many, many, many years. That's where our sun sits now as the main sequence star. We then enter the death phase. So as far as the end of a star's life cycle, this is going to depend on the mass of the star. If we consider small stars first of all, and our sun is a small star in the grand scheme of things, what's going to happen is it eventually gets to a point where it's going to cool and expand to become this thing called a red giant. And you can see in the top picture on the left hand side there, this is showing us what we mean by cool and expand. So we can see our sun, that little orange dot on the left of the picture, and a red giant next to it. That gives you some idea of how much we are expanding. As a result of this, we then end up with the outer layers breaking away to form a planetary nebula, and we're left with this white hot core of the star, which is called a white dwarf. And over time, that white dwarf is going to cool and fade. If we talk large stars, so these are ones with a much larger mass, they still expand and cool, but because they were large anyway, they become a red supergiant because they're going to be much larger than the red giants. They will explode as a supernova, and during the supernova, the core of the star actually gets crushed down by these huge gravitational forces to form this thing called a neutron star. And a neutron star is one that's going to spin really fast and send pulses of radio waves back to Earth. And because they're radio waves, we can detect them. And in fact, you can listen to a neutron star. If you do a search on YouTube for neutron star sounds, you can literally sit and listen to neutron stars spinning. If we have a big enough star, then that core gets crushed down even further into a tiny, tiny space. And that is a black hole. So what we're seeing there is the core just keeps getting crushed down into an incredibly small space to form this thing called a black hole, which has such a strong force of gravity that not even light can escape it, hence black hole. If there are bits you'd like to look at in more detail, then you have the P8 playlist on the channel you can use, your revision guides, and of course have a look at some of the past exam questions. Things like the sequencing of the bits of the star's life cycle come up. So do have a look to get a bit of a feel for the kinds of questions that come up there. And then of course, don't forget to join us again tomorrow for our next daily booster.